You guys hear me? Great, thank you. Cool. Okay, so less than a minute. Yeah. Okay, it's 8 o'clock, so let's get started. They probably won't be as long because we're only going to finish up chapter 7. Okay, so we're going to continue on with inferential statistics and hypothesis testing. Let's see. So the conditions that are required for a valid large sample hypothesis test for the mean are that we have a random sample is selected from the target population. Makes sense. And the sample size of n is larger than 30. It comes back to the central limit theorem. This condition guarantees that the test statistic that we draw is approximately normal due to the law of large numbers on central limit theory and how all distributions converge to the normal distribution. So that is those two main assumptions or requirements to run a hypothesis test. So there's a couple of possible conclusions for our test, as we talked about on Monday. The calculated test statistic falls in the rejection region. We can reject the null hypothesis and conclude that the alternative hypothesis is true. Like I said, we always reject the null. We never accept the alternative. So state that you are rejecting the null at the alpha level of significance. Remember that this confidence is in the testing process, not the particular result of a single test. If the test statistic does not fall in the rejection region, we conclude the sampling experiment does not provide sufficient evidence to reject the null hypothesis at the alpha level of significance. Generally, will not accept the null hypothesis unless the probability of beta or type 2 error has been calculated. We're going to talk a little bit about beta towards the end of class, but it's pretty laborious to calculate it out and not often used unless you're doing human subjects types research, but we'll talk about it a little in a moment. So let's do an example. You are a QC inspector. You want to find out if a new machine is making electrical cords to customer specification. So the average breaking strength of this electrical cord is 70 pounds. So that would be our mu value, right? So what we believe to be the true population mean. It has a standard deviation of 3.5 pounds. We're going to take a sample of 36 of these electrical cords, and we compute a sample mean, or an X-bar, of 69.7 pounds at the 0.05 significance level. So alpha is 0.05. So is there evidence that the machine is not meeting the average breaking strength? So I'm going to show you a little bit different way to calculate out our z-score. It'll be a little easier to do for the one sample hypothesis test since it's not really built well into Excel. But so we're going to need a few values. We have, our X-bar value, our mu, standard deviation, our sample size, and our alpha. So let's go pull those from no, let me put it there. There we go. All right, so now we can let things read. Okay, so our X-bar was 69.7. That's the sample mean, right? 69.7. Sorry, wasn't on. All right, so our mu So we believe, or we think it's 70 is the true population mean for the breaking strength of this electrical cord. We have a standard deviation of 3.5. We have a sample size of 36. And we are interested in an alpha 0.05, most common one we do. So first thing we're going to have to do is calculate out the z-score, right? We're going to use to compare to our critical value. And to do that, we are going to use the formula that is going to be our x bar, or sample mean. Our sample mean minus the population mean. We're going to divide that by standard deviation. Let's see, standard deviation divided by the square root of our sample size. Okay, so that gives us our z-score. It's just the formula for calculating out z-score based on the data that we're given. So we want to compare that z-score to our critical value for 0.05, right? This is a two-tailed test. So we're interested in the two tails. And I think we will calculate out one tail just so you can see that's not too different. So we're going to use the norms inverse. And it's going to take our probability, alpha is our probability that we're interested in. And for a two-tailed test, right, we have to divide that alpha into the two tails. So we're going to do this alpha 0.05 divided by 2. And that gives us 1.96 roughly, which hopefully you've memorized by now. And then for one-tailed, we're going to put all the area into one tail, right? So we're going to, all we have to do is select our alpha. So now we can compare these. Basically, we need the z-score to be higher than our critical value, right? And it's not. Thus, we conclude that we failed to reject the null hypothesis. Okay, so basically what we did. So our null hypothesis was that the true population mean mu was equal to 70. The alternative hypothesis, mu does not equal 70. What we were trying to prove with our hypothesis test. That our alpha level of significance of 0.05, sample size of 36. Our critical values are plus or minus 1.96. So to calculate out the test statistic, do this in Excel, x bar minus mu divided by the standard deviation divided by the square root of the sample size. So we got 0.51. That does not exceed 1.96. So there is no evidence that the average is not 70. So we failed to reject the null hypothesis. Okay, so that's basically just a review of what we did on Monday, but a different way of doing it, just the formula instead of using the data analysis tab. Okay, so continue on. We have focused on large sample size hypothesis testing, right? But we have a small sample size. We need to use the t-test, right? So we need to draw our test statistic from the t-distribution instead of the normal distribution. So everything's pretty similar. Our null hypothesis are saying that the true population mean is the true population mean, right? And then for one tail, we're going to say it's the alternative is either that the true population mean is less than what we found or it is greater than what we found. And then that's when we could reject the null hypothesis. The test statistic is found basically the same way, right? It's our sample mean minus our population mean divided by the standard deviation divided by the square root of n. Our rejection region is we find a t-statistic that is greater than our critical value, and we can reject the null. Otherwise, we would fail to reject the null. Using the student's t-distribution, we have to take into account the sample size, so we have to do n-1 degrees of freedom. n-1 because we're trying to estimate one variable, so that's why we have to compensate for that. So it's basically what I just said. Okay, so conditions required for a valid small sample size. It's selected from a random sample from the target population, and the population from which the sample is selected has a distribution that is approximately normal. So come back to this example that we did the other day. Technically, with 36 boxes, we can use the normal distribution, but we can still use the t-distribution because it is a relatively small sample size compared to all the cereal boxes in the world, right? So we have an average box that contains 368 grams of cereal. Take a random sample of 36 boxes, and we found that we're putting too much cereal in there, 372.5 grams. And there's a standard deviation of 12 grams. And we're interested in a 0.05 level of significance. So this, let's go another page. We're going to pull the same variables out like we did before, except now we're going to use the t-distribution instead of the normal distribution. So x bar, our mu, standard deviation, our sample size, and our alpha. So x bar is 372.5, mu 368, standard deviation of 12, sample size of 36, and level of significance alpha 0.05. So first we need to calculate out our t-statistic, which is the same way we calculate out our z-score. So we want to subtract x bar minus mu divided by standard deviation divided by the square root of our sample size. And we get a t-stat, or t-statistic of 2.25. This is a two-tailed test, so we can do critical and do the same thing. Critical for one, tailed. Let's do critical for a two-tailed. So that way we can have both of them ready. Basically, I'm teaching you how to build your own calculator. Okay, so for this one, we want to use t dot inverse. So you'll see that when we go to the two-tailed, we're going to use the other formula. But t inverse, we're going to take our probability of 0.05. Degrees of freedom is going to be n-1. So we get, technically, we can do absolute value on that. So let's do that. So we're doing a one-tailed test. 3.25 exceeds 1.68. So from a one-tailed perspective, we would say we can reject the null hypothesis. So let's see what happens with a two-tailed test, since that's what we're looking at right now. So it's going to be t dot inverse two-tailed. probability of alpha 0.05, degrees of freedom n minus 1, 2.03. So we can reject the null hypothesis because 2.25, our t-statistic exceeds our critical value of 2.03. So you see that here. Our null hypothesis, mu equals 368. Our alternative hypothesis, mu does not equal 368. An alpha of 0.05 level of significance. Degrees of freedom are n minus 1, so 36 minus 1 is 35. We calculated out our critical value from the t distribution. It's plus or minus 2.03 is what we got. Calculate our t statistic, x bar minus mu divided by the standard deviation divided by the square root of the sample size. We got 2.25. We can reject at an alpha of 0.05 significance. So there is evidence that the population average is not 368. So we reject the null hypothesis, and the quality control at the cereal box company should really be looked into. Okay, so let's do another example. You work for the FTC, the manufacturer of detergent claims. The mean weight of detergent is 3.25 pounds. You take a random sample of 64 containers. You calculate the sample average to be 3.238 pounds with a standard deviation of 0.117 pounds. At the 0.01 level of significance, is the manufacturer correct? So we can use the same spreadsheet we just used, right? So our x bar sample average was 3.238. Our mu was 3.25. Standard deviation is 0.117. Sample size 64. We're interested in at the 1% significance level. So calculates it all out for us. And should match 2.65, 2.65, negative 0.82. So our calculator works. So the null hypothesis was that the mean equals 3.25 pounds. The alternative hypothesis was that mu does not equal 3.25. And an alpha of 0.01. Slide got messed up. Our degrees of freedom is 64 minus 1, and minus 1 is 63. We pull our critical value for our student t distribution. We get plus or minus 2.656. Calculate out our t statistic, and we got 0.82, which does not exceed 2.65. So we do not reject at alpha 0.01. There is insufficient evidence to reject the null hypothesis, or we fail to reject the null hypothesis. Alright, let's see. So let's look at a one-tailed test. So is the average capacity of batteries less than 140 ampere hours? We take a random sample of batteries, 20 batteries, that had a mean of 138.47 and a standard deviation of 2.66. So we assume that the distribution is roughly normal, right? We have a small sample size, less than 30, so we have to use a t-test in this case. I want to know, is this significant at the 0.05 level? So here's our calculator again. In this case, our x bar sample mean is 138.47 ampere hours. U is 140. Standard deviation is 2.66. Sample size of 20. Alpha of 0.05. So we get a t statistic of 2.5 and a critical value of 1.72. So based on our test, we can reject null hypothesis. Our null was mu equal 140, or greater than or equal to 140. Alternative, mu is less than 140. Alpha at 0.05. Degrees of freedom is n minus 1. 20 minus 1 equals 19. We're looking at a less than, so we're looking at the lower tail. All the area of the critical or rejection region is in one tail. So we can reject the null because our t statistic exceeds our critical value. So we reject the null at 0.05. All right, so in the examples we've done so far, we were given, the sample mean and the standard deviation. So what happens if you're giving an array of data, which will be more likely in the real world? So what we will do is we'll input this data, 8, 11, 0, 4, 7, 8, 10, 5, 3. So let's see. Got all 10 values in there. You're a marketing analyst for Walmart. Walmart had teddy bears on sale last week. Weekly sales in hundreds of dollars. A bear sold in 10 stores was 8, 11, 0, 4, 7, 8, 10, 5, 8, 3. That's why we type this up. I want you to know at the level of 0.05, is there evidence that the average bear sales per month is more than 5? So we need to calculate out our values, right? So we know that mu is 5, right? So we need our sample mean. So let's use the average function for get an average of 6.4. Standard deviation, use our standard deviation function. The same set of data. 3.37. Sample size is 10. If you had more data and you didn't know, you can do the count function and it will count up your data for you. Do that just to double check. So we have 10. All right, so let's see. T statistical 1.3. Doesn't look like we're going to be able to reject the null hypothesis. All right, so but the null hypothesis was a mean is equal to 5. Our alternative was that the mean was greater than 5 at the 0.05 significance level. Degree of freedom is n minus 1 equals 9. So we can calculate out our critical value from the student t distribution at 1.83. Our t-stat was only 1.31, thus we do not reject at alpha 0.05. There is no evidence that the average is more than 5, so we fail to reject the null hypothesis. Okay, let's move on to proportions. Okay, so large sample test of hypothesis about P. So we have our null hypothesis that the true population proportion is equal to true population proportion, and we can have a one-tailed test in either direction, either that proportion, our sample proportion is less than the true population proportion, or it's greater than the true population proportion. Calculate out our test statistic. We're going to use the normal distribution, right? Because proportions are on the binomial distribution, but all distributions converge to the normal distribution, so we can use a z-score, assuming we have sufficient sample size. So to get that z-score, we're going to take our p-hat, which is the proportion we get from our sample, minus the true population proportion. We're going to divide that by the standard deviation of our sample. And we calculate that out by multiplying P times Q and dividing by the sample size. These are what are given to us. The P, or the proportion from the population. We find the Q side by subtracting 1 minus P. So, and of course, if our z-score exceeds our z alpha, then we will check the null. So, conditions required for a valid large sample hypothesis test for a proportion. It needs to be a random sample selected from a binomial population. So basically there's two proportions, right? P and Q. Whatever doesn't fall into P has to fall into Q. Sample size n is large. This condition is met if n times P is greater than 15 and n times Q is greater than 15. So we're still looking for a sample size of 30 total. But half of those need to be P and half of those need to be of Q. All right, so let's do a one proportion z-test example. So we have this box of cereal. Their packaging system produces 10% defective cereal boxes. Using a new system, a random sample of 200 boxes with 11 defects. Does the new system produce fewer defects at a 0.05 level of significance? Okay, so start a new sheet and we'll solve this problem. So we need p hat, right? So p hat is going to be the proportion of our sample. That's going to be equal to 11 divided by 200. We have a sample size of 200. Our p null, let's call it p0, was 10%. Plus our q null is going to be equal to 1 minus p null. Sample size of 200. And our alpha is 0.05. We need to calculate out our z-score. And we're going to use the formula that we just talked about. So it is p hat minus p null divided by the square root of p null times q null divided by the sample size. And that will give us our z-score. Now we need to compare to our critical range. So to get a one-tailed or two-tailed test, we need to use our norms inverse function. And we can do for two-tailed also. Same idea from our mean a couple of slides back. So it's going to be norms inverse alpha divided by 2 because it's in two tails. So you can see that our z-score exceeds our critical value, so we should be able to reject the null hypothesis. So our null hypothesis was that p was equal to 0.1. Our null was that p was less than 0.1. Our alternative at alpha 0.05, our sample size was 200. We calculated out our critical value, 1.645. And when we calculate our z-score, we get a value of 2.12, which is greater than 1.65, and thus we can reject at alpha equals 0.05. So there is evidence that we can reject the null hypothesis. Thus, the new system seems to be doing a better job. Okay, so let's do another example. You're an accounting manager. year-end audit showed 4% of transactions had errors. To implement new procedures, a random sample of 500 transactions had 25 errors. As proportion of incorrect transactions changed at the 0.05 level of significance. Okay, so I should be able to use the same calculator. Let's see. So this is going to be equal to 25 divided by 500. 25 errors in a random sample of 500. We have 4% for P null. We have random sample of 500. So we get a z-score of 1.14, which is less than our critical value, so we will fail to reject the null hypothesis. So our null hypothesis was that P was equal to 0.04. Alternative was that P does not equal 0.04. So it's two-tailed. We have alpha of 0.05, sample size of 500, critical value is plus or minus 1.96. We get a z-score of 1.14, and thus we fail to reject the null hypothesis. So Alright, so now we move on to giving a hypothesis test on a variance. Although many practical problems involve inferences about a population mean or proportion, it is sometimes of interest to make an inference about a population variance. Very rarely have I used a hypothesis test on a variance. So the null hypothesis is that the variance equals the true population variance, and then one-tailed, it's either less than or greater than the true. Now for this one, we have to use the chi-square distribution. So to get that test statistic, we have our n-1 times our sample variance. We're going to divide it by our population variance. And I call the other test, if our chi-square test statistic is greater than our critical value, then we can reject the null hypothesis. It's another one based on degrees of freedom. Two-tailed test we can do as well. It's either the null is going to be equal, and the alternative will be that it is not equal. So to run a variance, we need a random sample is selected from the target population. Population from which the sample is selected has a distribution that is approximately normal. Okay, so the chi-square distribution changes based on the degrees of freedom. It's this kind of lopsided curve. With 1 degree of freedom, it actually looks exponential. But as we increase the degrees of freedom, it starts to kind of flatten out, and the tails will get change their shape. Find the critical value. We'll talk about this, but I'm going to show you how to do it in Excel. You can read a chi-square table. So you have the number of degrees of freedom, and then your interest, the chi-square of like 0.1, 0.05, 0.025, and then you can get the critical value. So if we have an alternative hypothesis that the variance is greater than 0.7, we have a sample size of 3, we're interested in alpha of 0.05, and we get the degrees of freedom. We can 2. We're going to look in this row and go all the way over to the column that is for alpha 0.05, and we would get our critical value of 5.991. So if we want the other tail, the other side, the variance is less than 0.067, we're going to get this side, same idea. We're going to take 0.05 and subtract it from 1, so it's going to be 0.95. That'll give us this side. Okay, so let's do an example. Chi-square test is the variation in boxes of cereal measured by the variance equal to 15 grams. Random sample of 25 boxes had a standard deviation of 17.7 grams. Test at the 0.05 level of significance. So similar to the other population parameters we can do hypothesis tests on, we can do it on this as well. We're going to need the variance, our sample size, standard deviation, and our alpha. So it was given to us as 15 for the variance, sample size of 25, standard deviation of 17.7, with 0.05 level of significance. We're going to want to calculate our chi-square test statistic, and then we're going to get our critical value, critical chi value. All right, so we're going to input the formula. It's going to be equals to our sample size minus 1. That gives us our degree of freedom, right? So that times the standard deviation squared, because we want the sample variance. So I'll divide that by the variance. That will be our chi-square statistic that we're going to compare to our critical value. Now for this, we need to pull the critical value from the chi-square distribution. So we're going to have to use our chi-inverse function. So we're going to take our alpha value divided by 2. And our degrees of freedom, our sample size minus 1, and we get a value of 39.36, and 33.4 does not exceed 39.36, thus we fail to reject the null hypothesis at 0.05. So you can see the null hypothesis was the variance is equal to 15. The alternative hypothesis is that the variance does not equal 15 at alpha 0.05. Degrees of freedom is n minus 1. 25 minus 1 is 24. We are going to look at the upper tail. We calculated out that critical value of 39.36. Our test statistic, n minus 1 times the standard deviation, or that's the sample variance, divided by the variance squared. We get 33.42 as our test statistic, and because this value is not greater than that value, we fail to reject the null hypothesis. Okay, I just want to briefly talk about type 2 error. I think I pulled any calculation of the data or type 2 error off of the homework because it's very time consuming. Like I said, unless you're doing human subjects research, you're probably not going to do too much with power. So the type 2 error probability beta is calculated assuming that the null hypothesis is false because it is defined as the probability of accepting the null when it is false. Situation corresponding to accepting the null hypothesis and thereby risking a type 2 error is not generally as controllable. For that reason, we adopted a policy of non-rejection of the null when the test statistic does not fall in the rejection region, rather than risking an error of unknown magnitude. So to calculate beta for large sample size, we calculate the values of our x bar corresponding to the borders of the rejection region. There will be one border value for a one-tailed test, 2 for a two-tailed test. formula is one of the following corresponding to a test with a level of alpha. So we calculate this out, and the lower tailed. That's how you do it for upper and lower tailed. I'm not going to have you calculate it out, I don't think, so don't focus too much on it. Then we're going to specify the value of the alternative population, the population mean for the alternative hypothesis, for which the value of beta is to be calculated. And we're going to convert the border values to z-values using the alternative distribution with a mean of QA. General formula for that doesn't really change. We're going to sketch the alternative distribution centered at that mean, so we're going to look at both of them and calculate basically the area on both sides of that. Should have had a distribution to show that, but that's how you will find your beta value. So the power of a test, or the probability of rejecting a false null, is equal to 1 minus beta. It's used in determining test adequacy. It's affected by the true value of the population parameter, the alpha that you chose for your test, and the standard deviation and sample size of n. So basically, know that power is equal to 1 minus beta. I'm trying to simplify this part because, like I said, it's not going to be super useful unless you get into survey research and human subjects research and all that. But most of the time we don't focus too much on power because, like I said, we don't have too much control over it. Other than that, that is the end of chapter 7. So